I have here a definite integral, so I'm trying to find the area underneath the x squared graph from x equals 3 to x equals 5, so I have that here. And I want to break this down into its Riemann sum parts, or its rectangular parts, and then be able to add up the rectangles to estimate the area. Now, I can go from the integral further to the Riemann sum expression, and I can apply the limit as n goes to infinity to go back to the integral expression as well. So I can go either way. And in this case, what we're going to do is we're going to start with the integral expression and come up with the Riemann sum expression for this. Now, to do this, we need to work out the rectangular area. So I have my f of x times delta x. On my graph here, my f of x is going to be represented by the height of this graph. So if you notice where I've measured the height, that happens to be a right Riemann sum. And the delta x is going to be the width of that rectangle here. Okay, so when I multiply those two together, I get each rectangle. And if I sum up all the rectangles, I'm going to be able to get my Riemann sum area, okay, or my Riemann sum estimate of the exact area. So how are we going to do this? So the first thing we're going to do is we're going to establish the interval width, okay, which is our delta x, okay, which helps us establish delta x. So we want to come up with our delta x expression. To do that, we're going to work out our interval width, which we're going to call I. In this case, our interval width is from 3 to 5. So to get the delta x, I'm going to do 5 minus 3 to get my interval width of 2 and divide it by n. And we're just going to leave it as n because we want to be able to change the number of rectangles that we might want to use to add up this area. So that becomes our delta x, or our dx, and our height is going to be x squared. Now, to establish the height in terms of n, we need to come up with an expression for our x in terms of n. So to get the expression for x, we need to figure out the x coordinate. So we're going to start with k equals 1. So notice that our sigma form has a k value here. We're going to count from 1, 2, 3, 4, successively up to n. So let's start at k equals 1 to get the right-hand coordinate. To get the right-hand coordinate, we're going to start at a, our starting value. In this case, it's going to be 3. And we're going to add 1 interval width, or 1 delta x. So if we start at a and add 1 delta x, I'm going to end up with a plus 2 over n, because we've established 2 over n is our delta x expression. So that's going to be our starting point. And for each successive coordinate, we're just going to add 1 more delta x, or 1 more 2 over n. So that's why we get this expression here. We're going to start at a, and for every k, we're going to add a delta x. And once we've established our expression for x, in this case, our k, or I've notated as x sub k, once I've established that, what I can do is I can now plug that into the x in our function. In this case, our function is x squared. So notice that inside the x squared is my a plus 2k over n expression. That represents our x. We square that to get the height. We're going to multiply that by our 2 over n. Again, this represents our delta x. Okay, so that's our dx. And this portion here represents our f of x. So now we have our sigma expression that we're going to use. If I let the n go to infinity, then we have an infinite number of rectangles that will give us the exact integral. We can let n be any finite value to calculate the different number of rectangles that we might want to accommodate. So at this point, I want to check my bounds. I want to make sure that I'm going to start at a equals 3 and end at b equals 5. So to check the bounds, what I'm going to do is I'm going to plug in my k value starting at 1. And in this case, I'm going to let my limit go to infinity. And when I do that, I have 2 times 1 divided by infinity. Well, that's going to just give me the starting value. When k equals 1, I'm going to start at 3. My ending point should be when k goes to infinity. So n is infinite. Okay, as we allow k to go to infinity, we're going to choose infinity in here. So we have infinity divided by infinity. I'm just going to write that in. K is going to be infinite. N is infinite. This is a linear term divided by linear term. So we end up with 3 plus 2, and that gives us our n value when k is infinite in this case. As we let n go to infinity, we're going to have our last term, our end point equaling 5. Now, in this case, we let it equal infinity, but as long as k and n are equivalent, we're going to have our starting position going to be, those terms will always cancel out. So at this point, we now can see that our bounds are correct. We're going to start at 3, end at 5, and then we can come up with our expression here. This expression represents the exact value, so this is going to be equal to the integral form of x squared dx from 3 to 5. Now, if we let n be a finite value, we can calculate this will accommodate any n number of rectangles that we might want to use.